All right, folks. So here we are at the computer, and I want you to see that what you've got here basically is a much, much better look at what we just were doing on the chalkboard, but we've got a technological view of it. Here's the actual function up here that we were playing with. They've got f of x notation. I was calling that p for probability, and they're calling this x, and I was calling that z. That is completely irrelevant. It does not matter at all. They're just variable names. But you've got your little beautiful bell curve right here, which is the important thing. That's the function that's being generated by that equation. Okay, endpoints, number of intervals, and method. We'll get to all those in time. Left and right endpoints, we were at -3. Clearly, this allows you to adjust any that you want. I want to keep it at -3. That's -3 standard deviations. Excuse me, not -3.4, -3. Can I get to it? There it is. So -3 up to +3. That's the one right here. And I'm going to keep it there for now, and then we're going to change it later. Number of intervals. So when I did this, I did it as number of trapezoids. How many trapezoids I broke the bell curve up into. This is not using trapezoids, and I'll explain why momentarily. It's using rectangles. So it starts with 1 and allows us to break them into as many rectangles as we'd like. So we'll start with 1 and go from there. This is the method is the interesting thing. Method is left hand, right hand, or midpoint. And I'm going to leave that alone for now and just say, and it'll make more sense when we start breaking this thing into actual regions, but I want to say that the trapezoid method I showed you, while it is the most intuitive, is not the one that's normally taught in calculus classrooms. And for the life of me, I can't remember why, but it doesn't matter anyway, and we'll get to why in time. So hang tight on that. Down here, this sum right here is going to be equal to the area, quote unquote, under the curve that's being approximated. And I want you to watch that and watch how it kind of becomes 1 over time. That's the fun part of this. The rest of this we can ignore. Right now it's a 2.4. Now hopefully you realize why it's a 2.4. If we're trying to estimate this curve with this rectangle, we're doing a hell of a crappy job because we've overestimated it. We've got all this extra area out here, and that extra area corresponds to roughly 140% of the actual curve. So obviously, the number of intervals is not good at 1. Let's slide it up to, I'll go to 2 first. Now what 2 does is it puts one rectangle here and one rectangle here. And do you see how the rectangle crosses in the middle between 0 and 3? That's when they say midpoint sum. They're making the rectangle pass through the middle of the curve. If you go with the right-hand sum, it would look like that. The left-hand sum would go like that. If I had to choose these 3, I'm going to keep it at the middle. And there's a good reason for that, and we'll get to it as we go. I can't draw trapezoids on this because it's not set up for trapezoid sums, but you can see what would happen if we did trapezoids. We would draw a point here, and then way out here to 3, and then we'd find the area of that trapezoid. Not a big deal, not a huge deal at all as far as that goes. We're gonna just ignore that and kind of run with these. And like I said before, it's not going to matter anyway. So let's increase it to 3 regions. Okay, there's 3. So you see what's happening now? We've got one rectangle over here that's 2 wide, one rectangle here that's 2 wide, and one rectangle here that's 2 wide. So we're beginning to kind of fill the curve better. You're beginning to see that this area here is kind of equal to this area here, but we've got this little extra bit down here. So if we scroll down and check the area, look, the area is still a little bit above 100%. But again, not to worry. We're not done refining yet. Let's increase to 4. Or 5. We'll go to 4 first. So now you've got 1 here, 1 here, 1 here, and 1 here. And now notice the area is below 100%, which means we've got too much area on the outside of the curve and not enough inside. But that's okay. We can keep increasing the number of intervals. I skipped over 5 and went to 6. We can go to 7. We can go to 8, and you see what's happening? The more intervals we have, let's pop it out here to 14. That now means you have 1, 2, 3, 4, 5, 6, and then 7, which is very hard to see, but it's way down here. And then you've got 1, 2, 3, 4, 5, 6, 7, way down here. And it's actually kind of cool. I just happened to stop at a place where the area sums to 99.75. And if I look back at my chalkboard, we got 99.77 with 12 trapezoid rectangles. So we're pretty close to where we were. But what's so great about using technology is we can just keep increasing the number of rectangles. And what you're beginning to see is you're beginning to see that that curve is really and truly filling in. This tool allows us to fill it with 100 rectangles. So there they are. There's all 100 rectangles. You can kind of see them in there. You can kind of, if I can zoom in right here and take a look. Yeah, you can tell the rectangles are still there, can't you? Whoops. There they are. 1, 2, 3, 4. But look, all these regions out here and down here are kind of balancing each other out. So let's zoom back out and take a look. Okay, so there's your -3 to 3 region. But the thing about it is this normal curve doesn't stop at -3 and 3, right? This thing goes on forever left and forever right. Now, this tool only allows me to drop this down to -10 and this up to +10. So now we have increased the number of, that didn't go to 10. There it did. Now notice the rectangles just got a little bit more manky. They got a little bit more manky because it's the same number of rectangles now, but we're over a much larger region. We are now going all the way from -10 to 10. Now some of you, when you're looking at this, you're like, wait a minute, there's nothing down there. There is something down there. It's just an extraordinarily small mathematical amount of area that's down there. So if we slide down and take a look, you might, I don't know if you can see this or not, but this right here tells us that that integral, all those rectangles, have added up to 1. Now, the more mathematically you analyze this, you realize it's actually not exactly equal to 1 because there is curve left of -10 and right of +10. However, this is we're at 0.9999999, and however many nines there are in this computation, we are at that many nines. So what you've got here is you've got a beautiful calculus-driven explanation as to why the sum under this bell curve has to be 1, which stands for 100%, which stands for the sum of all possible probabilities on a normal distribution, which is kind of cool. So you've had a taste of calculus, which is really just a whole lot of geometry on considerably shrinking figures. And I hope it makes a little more sense to you now, what we do in class. Be well. We'll see you there.